Cool. Okay. Yeah, that checks out because I think you said that it was with the DOE, right?
Yeah, that's right.
Yeah. So, just so students know, so there are research opportunities that you can apply to, and some have. Sorry, I know I'm cutting it out. Most of them have deadlines that are kind of early in the winter, so there's something you got to get on top of. They tend to be those emails that we all just delete instead of actually reading through. Those are the opportunities that you want to look out for. But again, some of them are in fact paid opportunities. It's a great way to spend your summer. I know that we have at Fresno City program that puts students into internships in the Valley. The Central Valley is actually a pretty big area for chemistry because we have so much agriculture and so much environmental science going around. So there's a lot of these like research opportunities, internships that you can have, some of which are paid, which is great. I mean, you can put it on your resume as opposed to if you're working at Starbucks. Just sort of a good way to go about sort of advancing your career and, for something you can end up putting on your resume as well. And was that kind of the turning point in your education as well, getting involved in research?
Yeah, so I decided the next summer to apply for a chemistry position. So I got one at the National Renewable Energy Lab, which is also a Department of Energy internship. And I think what that was really important for me is that that summer we got to do research on sustainable energy and just basically advancing technology to, for climate change and for reducing greenhouse emissions and for recycling plastics. And I just thought, wow, I could really use my degree and do something that might have an impact. So that was very exciting for me.
Yeah, I definitely had like a turning point in my education career as well when I got involved in research. Having been a teacher for a while, my experience, most students who are the most motivated are the ones that know exactly what they want to do afterwards with their degree. And for the sciences, that's a little bit harder to do. Usually your future is a little fuzzy for a bit. And getting involved in research, all of a sudden you how this is going to be applicable in the future. And you just kind of take your classes a little bit more seriously. You just kind of really are there to learn the material as opposed to just get through and get your grade. And that makes a huge difference on, your education as an undergrad. Um, you know, Grads that the most that you can do with your time here is not just get your degree, but all the other little stuff that you have the opportunity to do here at this college, right? So getting involved in these research projects that are going on, taking advantage of these little programs and stuff like that that help further your career, that's really, really beneficial for you in the future. Cool. So we had a few questions about like mentors that you had along the way. Is there anybody, like when I say mentor, is there anybody that comes to mind as playing a really critical role in your development as a scientist?
Wow, I think, some of the TAs I had as an undergraduate were really influential to me. And my graduate and postdoctoral advisors were very encouraging. I think, part of the hard part about learning to become a scientist is there's a lot of uncertainty, and part of part of the process of becoming a scientist is that you feel dumb a lot. And the point is that, even though you'll feel dumb because you have to if you're learning things new, right? It's like one of those things where if you're not, you know, if you don't feel like that ever, then you're probably not pushing yourself hard enough or trying to, progress enough. But it's nice to have people that are always giving you sort of the reality check that like, yes, this is normal, this is fine. It's not like you're not good at this, but you just have to like keep working at it and things. And so that was really helpful, I think, having those types of mentors that, you're just gonna feel like a failure sometimes when you're going through the process. And it's good to have people to give you the reality check, which is that, this is part of the normal growth of improving yourself and learning more and trying new things and getting new techniques down and things like that.
Yeah, I mean, you're definitely going to fail more times than you succeed.
Yeah.
Part of the game. Yeah, I mean, same for me. I can definitely think of like the word mentor, somebody just directly comes to mind, and that was my undergraduate research advisor. And I got involved in a little bit of a different way. I didn't respond to one of those emails that, we always delete. I kind of just emailed a professor out of the blue and was like, hey, I've looked on the website. I think what you're doing is really interesting. Can I come by and talk to you? Just sort of chatted about his research, and that led to an intern position in that lab that then turned into, all the way into my graduate thesis. So it's sort of just like having the courage to just sort of see what's being done here at this college and reaching out to those people that are doing something that you think is cool can hugely influence. Yeah, networking is always a little bit hard. Your professors here are sort of your first step to getting that opportunity. So I think next question is kind of just like trying to paint students a picture of like what the path is to go from being an undergraduate student to a research professor. Like what were the steps along the way that you had to do to get there?
So I knew I wanted to do research when after those undergraduate experiences. So I went and got my PhD. And then I decided I wanted to go back to a national lab because that's where I did all these really cool summer experiences. So I postdoced at one, the Pacific Northwest National Lab. It's in Eastern Oregon. And that was really fun. And I got hired as a scientist there, and I did that for several years. And it sort of was a little bit circuitous that later I was giving talks at a meeting, and someone suggested I apply to UC Irvine for a position. And it was, it was intimidating to me. From my point of view, all the people that went on to become professors were like, I felt like much smarter than me and much more accomplished than me. But I applied and I got it. And it was really good to have that experience because it's a big learning curve. But I think it gave me the confidence to do it. But it's, a lot of times I think it's perfectly normal to not know along the way what you're going to do. I mean, when I was in grad school, I went from, scientist to patent lawyer to like consultant, because there's a lot of jobs you can do with a PhD. Necessarily, if you decide you don't want to stay exactly in research science, it does open a lot of other doors to you. So then, I explored all those options and um, before I sort of settled on wanting to continue to do research.
Yeah. So I mean, yeah. So the very first step, right, is to go and get your PhD. For me, that was why I got involved in research was because I had decided that I wanted a PhD. I went to some seminar and they just were running the numbers about what your starting salary would be with a bachelor's in chemistry versus a PhD, and I was like, man, I want that extra 40 grand starting increase, please. Thank you. So that's what I got involved in research for was to kind of like help do that. But that's the step is to go and get your PhD. In science, it's great versus other sort of higher degrees, a medical degree, in that they pay for you to get your PhD. So you get a little stipend, you don't have to pay tuition. It's kind of your first earliest job is to just be a student and to work and to get your PhD. And then you go on and usually you go on and you do something called a postdoc, which is after you have your doctorate, but you're still just being like a full-time researcher. And that's a pretty natural like next step. There actually, I feel like I know a lot of people that have done more than one, kind of jumping around before sort of landing in their particular research field. And then you said you applied to UC Irvine. Like, what was it? I believe it was something about like your specialty that kind of fit into that department really well. Is that the case?
Yeah, they were looking for someone that was more interested in energy and sustainability, inorganic chemistry, electrochemistry. And there's, at the time there weren't a lot of people that did that kind of work. So I think I also looked out. But sometimes it's just opportunities, right? Like I didn't plan this out ahead of time, but the opportunity presented itself. So I think I was very fortunate in that respect to have that. But yes, I definitely encourage that. Like, I teach a lot of undergraduates here that are first generation students, and they said I can't afford to go to graduate school and get my PhD. What are you talking about? And I'm like, well, it is paid for. It's not a lot of money, but if you decide you want to continue to get your PhD, your tuition is paid for, and you get a small stipend to live off of, so you don't have to go into debt or take out a student loan or anything. And so it's actually a pretty good deal when you think about it.
Yeah, it is not a lot of money. You are
Yeah, you're not going to be rich, but you get that salary bump after you're done, I guess.
and then where you get your degree matters a lot too, because being in the Bay Area, that was really expensive on.
Yeah, that's true.
Anyways, they do pay for you to get it, which is a big sort of, incentive to go ahead and take that extra step. But yeah, a research professorship is a pretty difficult position to get, in part because we're not opening up new colleges every day, right? So like faculties tend not to grow too terribly much. And so you're kind of waiting for turnover. So sounds like you got pretty lucky with them looking for that particular field of research, which is probably the best way to do it, is to sort of be in a high demand field like, researching renewables and stuff like that. And then so you go on to get this professorship, and then there's a tenure process as well, right?
Mhm.
Yeah, and
Yeah. So, oh, go ahead.
so from students, I think the perspective of tenure just means that you can never be fired. Do you have insight into that?
Well, I wouldn't say never, but you would have to really screw up, I think, a little bit. So yeah, you typically, the way faculty works at most institutions is that you have some time period. For us, it's 5 years, where you show that you can establish a research program and you can get funding and train students, and that you're, good in the classroom and all that stuff. And then if all those, you check all those boxes, then you can earn tenure. Often they ask people outside in your field, outside university in your field, that say, is this person making impact in this area of research, just to get a second opinion on it. But yeah, and then you get tenure, and then it is, we still have a lot of responsibilities. We have teacher classes. We, are expected to take students and continue our research programs. But the evaluation is, it's not easy to fire somebody, I guess, in that position.
Yeah, I think it's more like the administration has a harder time getting rid of you. You still have like an employment contract that if you are in violation of that, that's not good. You're going to get in trouble. But
Yeah.
yeah, it is actually kind of an interesting history of, why it exists in the first place. When colleges sort of started out, the only people that were employed at the college were professors, people who taught. And then as these colleges got bigger and bigger, they started saying, okay, well, we need an admin department and we need a registration department and that sort of stuff. And apparently the balance got sort of out of whack where the admins started dictating what professors should be teaching. And that's when tenure sort of came into place, because there's this whole theory in higher education that being where we are in our field, we deserve to get to decide how to teach something. And so that's kind of what the thing, why this system of tenure exists in the first place. One more thing that I just want to touch on that Dr. Yang had mentioned was this idea of like not feeling smart enough. I can't tell you how much this like imposter syndrome part of the name of the game of being a scientist, because your intellect is kind of your bread and butter, and that's what you're doing. And again, you fail a lot more than you succeed. So it's just inevitable that you are always worried about other people being smarter than you. And that's really just not the case. I mean, if you guys are here where you are plenty smart enough. Having gone to, when I got my job at Stanford, I was so scared that I was going to walk in there and just be the dumbest person in the room all of a sudden. And I realized that like everybody in there is smart. That's not really it. The difference that separates them is just who's willing to work harder. Like who's willing to really put in the hard work. That's what's going to dictate your success. Everybody in here is smart enough to be going and doing research. Okay, cool. So let's switch gears and talk about the climate change aspect of things here. I know you're not a climate scientist, but of course your research revolves. So I was wondering if you could just like briefly summarize, in your view, what is the climate crisis that we're going through right now?
Ooh, well, we've emitted many, many gigatons of CO2 since the industrial era that did not exist in the atmosphere prior to the industrial era, except through some periods of history where we actually had pretty significantly different climates than we have now. I think one thing that's interesting to note when people say like, oh, it's not like our climate has always been exactly the way it is now. It hasn't, but it's been remarkably stable for about 10,000 years, which happens to be like human history, right? So we all have developed our cities and, next to the ocean and things like that based on this very steady 10,000 year climate. And now we're changing it really, really quickly. So it's not that this has never existed on Earth, but it's never existed with people on Earth. So that's why it's a little bit scary, right? Because this is how all of our cities have been built and all of our infrastructure and all the animals that we depend on. Um, so I was very interested in this even in the 90s when I was in high school and undergraduate, which is why I wanted to do research on it. And we really wanted to think about trying to use other sources of energy, but then of course that's not easy for various reasons. Solar is intermittent and other factors. And so, what are the other technologies that we need to develop with all these other things so that we can really see a way to transform our energy infrastructure completely in a way that does not rely on fossil fuels anymore?
Yeah, I mean, I think that that's a good point, that a lot of like the dismissiveness that you hear around climate change has to do with like the fact that yes, CO2 levels have been higher and yes, the planet's been warmer and colder, but within the span of human history, as mentioned, it's been remarkably stable. And so yeah, it's the pace at which things are changing that's getting surprising. And so are you optimistic, pessimistic about how humanity's dealing with this problem?
I'm more optimistic now. So one of my colleagues in environmental earth science, which is one of the departments here, gave a talk last week about climate change mitigation. He was part of a White House science advisor group to basically talk about, what are the ways that we can mitigate? How do we reach our goals? Because the thing is that like companies and countries have been promising all kinds of like reductions for the last 2 decades. They almost never meet them, right? And that's the whole thing, is that like you can promise all you want, but if you actually don't hit your targets, it doesn't do very much. And so basically they said, look, if you really want to meet these aggressive targets by the current administration, these are the things that you can do. And I think the optimistic part of that was that he pointed out that at least for the near term targets like 2030, um, we can probably do it with technology we have now. We just need to do it. It's not, whether it's incentives or government policies, but we just need to invest in it, and it can be done. It's not like we have to invent something new or develop some new technology. Part of the current targets is to get to net zero by 2050. That will require some new technology, but if we again start investing now, we can probably hit those. So I think in the end the message was optimistic, that like it's not like we don't know how to do this, we just have to do it. And I think that was kind of encouraging to know that, it's not an impossible task. It's something that can be done. It just requires the will to do it.
And there was sort of recent climate legislation that was passed earlier. Do you feel like that was a step in the right direction, or kind of just I don't know, a whiff?
Yeah, so the Inflation Reduction Act, it sounds like it's about inflation, but there was an enormous amount of energy policy in that, both in incentives and infrastructure, and I think many people have called it probably the most impactful legislation in climate in the history of our country, which is a big deal. And so that has really spurred on and really been a game changer in a lot of different industries, right? Because in the end, whether or not an industry will adopt a method that is greener or emits less, in the end, it's money, right? And so if you have incentives for them to do this, then they're more likely to do it. So it's been very impactful, and it actually has changed a lot of the investment in by different companies. Also having a price on carbon, right? If you think about, if it's free to emit carbon, there's zero incentive to not emit carbon, right? If that's the cheapest way of doing things, and so putting a price on things is basically a way to incentivize companies to really think about ways to reduce their emissions, especially if they can do so cheaply.
And so, what do you think? And so I guess that kind of segues. Do you think that incentive is really the thing that's the biggest challenge towards creating renewable energy sources? So really government policy to incentivize this sort of thing?
I think that an investment. So don't know if people have heard about this, but in so the part of the new administration is they put funding for 7 hydrogen hubs, which is a way to basically develop more cheaper versions of cheaper ways of producing hydrogen, which is really game changing in a lot of different industries to reduce greenhouse emissions. And California got one of these. It's $1 billion. $1 billion sounds like an enormous amount of money, which it is. But a lot of that is for infrastructure. So, a lot of this research goes to R&D, and it's like maybe it doesn't go anywhere. But this is actually like, how do we build pipelines? How do we build plants? How do we build all the things that we need to like really see this come to a reality? So this was just announced in the last 6 months that California received one of these hubs. They're called hydrogen hubs, that will really invest in building this infrastructure to see what we can do.
And what is it making the hydrogen out of?
Water, ideally. Yeah. So it's electrolysis of water.
Yeah. So,
Yeah.
the bottom line being like, right, fossil fuels, how we got so addicted to it is because breaking those carbon hydrogen bonds releases a ton of energy. And that's kind of what we've been taking advantage of in burning these fossil fuels. Hydrogen also will release a ton of energy when you break that bond. But the byproduct is water, so not as damaging to the environment. So that's the whole hydrogen fuel kick that you hear about. They sort of had hydrogen vehicles that kind of seemed to have fizzled out just because the electric car came along and kind of dominated. And that was a pretty big bright spot in the fight on climate change as well. That was not something that seemed like it was going to be able to happen, 10 years ago or so. So yeah.
Yeah, for sure. Having the battery technology to do that has been a very recent development.
And do you have any knowledge on biofuels as an alternative to fossil fuels, or is that a little too outside your realm?
So actually, there's a company that has scaled quite a bit across the world, um, called LanzaTech. If you guys look it up, they take CO2 emissions from like steel manufacturing and cement plants. I think we'll see steel, which is like 5% of the world's CO2 emissions. And they basically feed it to genetically engineered microbes that can turn it into jet fuel. And so this is actually now used in all airplanes at LAX, not completely, but at first, some of the airlines, sort of commissioned that we want to buy so many gallons of this, LanzaTech fuel. And in the way the fueling works at LAX, they're like, well, everyone has to use it because we can't just have this one airline use it. So some fraction of all flights that go out of LAX, that their fuel is from basically emissions. So you're recycling that emissions, and then of course it gets emitted as CO2 again. But it started out with CO2 that would have been
Right.
emitted otherwise. So you have the emission basically.
Yeah, okay, cool. And then I know that this is outside your expertise, but just curious, do you have any strong opinions about nuclear energy? It seems
Oh yeah, it's interesting. Yeah, no, I think it's I think it's part of a green. So I know enough people aren't excited about it because it's scary. But it's hard actually if you look at the numbers, it's hard to get to net zero without it. Let's put it that way.
it seems like a hugely underrated, or I don't know why it's not something that's being pursued a little bit more aggressively as an alternative. But I do get that, there have been these disasters that make it a lot more scary. But, just don't build them on a fault line or, next to where a
And
tsunami.
they are a lot safer. I mean, the unfortunate thing is that with every accident they learn to be safer. Like it's not really, it's hard to say that about nuclear, but it's true that, when you read about I just watched that documentary Chernobyl on HBO. It's like they do learn a lot every time something like that happens on how to make it safer. I mean, I'm not, maybe not everyone feels so comfortable with that, but it is a way basically of getting carbon neutral a lot faster.
Yeah, I agree. Okay. So transitioning to like your specific research, your presentation was sort of broken into two main topics. The first one being utilizing the electrocatalyst to convert CO2 to formate and vice versa. I was just wondering if you could, kind of just briefly remind students of, this aspect of your research, just a brief summary, and any new information that you have sort of learned since the presentation was recorded.
I'm sorry, which aspect was it again? I missed it.
The electrocatalyst to
Oh
convert.
yeah, yeah. So we're still working on that. So one thing that is new since I gave that presentation is that we were my lab and a couple other ones in a collaboration were actually awarded a Department of Energy grant to do integrated carbon capture and conversion. So instead of converting pure streams of CO2, we now try to convert dirty streams of CO2, which is actually how they exist in real life. So we've been learning how to basically find better ways of capturing it and then directly converting it into different fuels or chemicals.
And so this is sort of ultimately like a CO2 fixation method, because I know that there was some sort of idea that like, oh, by creating this super flat energy landscape and being able to make this reaction very reversible, that there could be sort of another avenue of almost like a CO2 battery that you could create from this sort of thing. So I guess my question is like, what would be the application of this research that you would see in the real world as you envision it?
That's a good question. So one of the things that we developed was a reversible catalyst to convert CO2 to formate. And that was interesting in the context of making a CO2 battery. So basically, instead of using the normal analytes, catholytes that you use, you just convert CO2 to formate back and forth again to like both store energy and get it out again. So we patented that at the time a few years ago when we developed that in the lab. And then I was contacted by the Navy a few months ago, and they were interested in exploring that further. And then there's an echo now, I think, in the room, but yeah. So anyway, it was very interesting because um, the Navy is very interested because when they need to use batteries, they don't want to ship a heavy battery. But if there's a way that you could basically make a battery out of CO2 from the air, that would be a lot more useful to them. And so they were very intrigued by this idea, and they basically have been talking to me about ways to try to push that technology a little further and actually make a device with it.
Is the patents on the platinum catalyst?
Yes.
Cool.
Yeah.
Um, So, I mean, platinum doesn't sound like a cheap material to use. Is there sort of a significant cost barrier to kind of like implementing this on a large scale?
So it's true that the platinum is not cheap. When I've talked to people about this that work in that flow battery field, um, they are more concerned with the cost of the organic solvent, the acetonitrile, than they are with the catalyst, because the catalyst they only need a small amount of, right? Because it's a catalyst. Um, than they are with but they basically said if you want something that's cheap commercial, it should be a cheaper catalyst, plus it should be in water, which is a lot cheaper than an organic solvent. But it's interesting with the military application or the Navy application because they don't care because they can spend a lot of money as long as they don't have to ship, something heavy to some remote location. They're okay with the fact that you're, moving platinum there.
And and so then why platinum? Like out of all the transition metal, I don't know. I think that we sort of think of platinum as being this inert metal. Was this just kind of trial and error and it worked, or is there something about platinum that makes it ideal for this?
Yeah, the properties and the energetics of platinum just work better for that reversible reaction. It and we have tried to replicate it with nickel, right? If you go one up in the periodic table, we try to get nickel to behave the same, and we haven't quite gotten there yet. So it is unfortunate that it is expensive metal. This is something that's very, unfortunately, very common in a lot of catalysts, is that a lot of times the best things are metals that are rare and expensive. Like if you have ever bought a catalytic converter or you've had to get a new one, or you've heard about them getting stolen, there's a reason. It's because they typically are very expensive metals. And so unfortunately, they tend to be the best ones.
And so it's other metals, if I'm sort of understanding, there's other metals that might work just as well at, converting CO2 to formate. It's just the reversibility aspect of it.
Yeah, yeah,
Reversibility aspect of it, the fact that you don't have this like flat free energy landscape, but one that's very tilted in one direction or the other.
yeah, that's correct.
Gotcha. But that would still be good for the carbon fixation aspect of it, no?
Yes, that's correct. Yes, absolutely.
And is there research being done to kind of explore that as, whatever, the highest free energy reaction possible to just super favorably fix CO2? Is that a research area that's kind of fruitful right now? It's not something that
Yeah, so there are companies. There's one that came out of Stanford actually that was called 12, and they are trying to do CO2 electrolysis and take CO2 to fuels effectively, or ethylene, which is an important precursor to polymers. So, all the plastics that you use in everyday life, which is obviously, we do need plastics. Right now, they all come from fossil fuels. And the reason why plastic is so cheap that we single use them and throw them away is because they tend to be the part of fossil fuels that we don't, need in our car, right? So they basically now make plastics with them. And if you envision a future where we're no longer refining oil and we're not getting these light, hydrocarbons, olefins that we can use to make plastics, and we need to find an alternative source for that carbon. And so one way to do that is from CO2 from the air, for example. We can make the carbon precursors that we need to make plastics. And so a very common product for some CO2 electrolysis is ethylene, which is, polyethylene, which is on all your plastic bags and everything. So you can replace that instead of being an oil product, basically a CO2 from air product. So I mean, we cannot replace carbon. Actually, it's interesting that, very for a long time people were talking about decarbonization. And as some people pointed out, carbon is an absolutely critical part of our materials, batteries, carbon fibers, airplanes. And so it's like we need to defossilize, but we don't necessarily need to decarbonize. We just need to find another source of carbon that isn't from the ground. And that's a different technology problem to solve.
that's actually super fascinating, kind of paints a picture of just how complex the challenge is. Because, I mean, you're basically saying in a world without fossil fuels, that sounds great because we have no CO2 emissions, but it also means that the price of plastic is going to quadruple or whatever because we don't have these cheap byproducts to make it from. And so then thinking ahead about like, okay, well, where is that going to come from is just another sort of tangential challenge that we have here. I'm sure there's a million examples of that, of this, kind of unexpected repercussions of decarbonizing, or at
Yeah.
least, like you said, getting away from fossil fuels. Yeah, that's cool. So then switching gears to the other aspect of the research, the CO2 condensation. Again, could you just start by just giving us a brief summary and then letting us know of any new sort of moves that have happened in that field as well?
Yeah, so one of the research projects in my group is to find better ways to concentrate CO2 from dilute sources. And right now, the way that it's done is incredibly inefficient. It's like terribly, terribly inefficient, actually. So the way that they do it right now, when they did a pilot plant, is that in order to capture the CO2 from a ton of coal, you need to burn another quarter ton of coal to then, so it's basically this very inefficient process to do so. And so we've been trying to find more efficient ways to do that. We try to use electricity to do it instead of thermal cycles, which is more common because they have much higher potential efficiencies associated with them. Plus, you can do it at room temperature. So we've worked on that for a couple years now. We've had some success in that. And we're trying to pilot some of that work now. So an interesting direction of that is that, when we first started doing this, I started talking to fossil fuel companies and other places that emit a lot of CO2 from their flue gases, which is basically exhaust gas. And I said, can we apply this technology to what you're doing? And it was interesting. They said, not really. And the reason for that is because they have so much process heat, which is just waste heat from their industrial processes, that they use that. And so they would have to re-engineer the whole thing to do electricity instead. So then I got really interested in the last year about coupling to HVAC systems because HVAC systems move a lot of air. You have to move a lot of air to capture a ton of CO2 because it's still, at 400 ppm. So we've been trying to work with different companies there to see whether or not we can couple our CO2 capture with HVAC, which it's just sort of a funny thing. I've learned a lot about HVAC in the last year, but it's sort of an interesting application that doesn't require heat or doesn't have a heat source. So it really plays up the advantages of doing electrochemically.
And so, why condense the CO2 in the first place? Just to sort of capture it and keep it in a place? Or is there some other motivation behind the desire to have this condensed CO2?
So I think in the end, we hope to sequester a lot of it, right? And it's hard to sequester from air because it's so dilute that some of the ways that they try to mineralize it to sort of do permanent removal just takes too long. So if you start with concentrated CO2, it's a little bit faster. But also, if we want to start thinking about recycling CO2 as a carbon precursor, we also want to start with concentrated streams. It just makes everything more efficient downstream. So these are the different reasons why we want to be able to basically extract it. Because in the end, the goal right now is by 2050 to be carbon zero, which means that we're no longer emitting or have net zero emissions. But after 2050, the idea is that we'll go carbon negative, which means that, by 2050, we might be closer to 500 ppm, and maybe we want to try to get back down to those pre-industrial levels that are 285, 300. And to do that, we need to do large scale carbon removal.
And so, first of all, do you think that goals like that's something that you could really see happening as being net zero by 2050?
I think that the talk that I heard last week from my colleague is basically like it's doable if we have the will to do it.
Which is
So I mean that was sort of encouraging, I guess. It's not like hopeless, like no, there's no way.
right.
Yeah.
It can be done. It's just if we have the functioning, powers that be that
Right.
put policies.
Yeah.
So I guess two things. You were talking about, again, condensing the CO2, just to sort of have it be condensed and out of the atmosphere. But also, I guess, to then, as you were saying, the company that came out of Stanford 12 that, is thinking about our sources of carbon that we need for the future, that would be there too.
Mm-hmm.
And so if you have all this stored CO2, where do you put it? Do you just envision fields of tanks in the desert somewhere?
Yeah, so a lot of the research, I'm not an expert in this area, but there is a lot of research into permanent sequestration. So there is mineralization, and actually one of the companies in the Bay Area also is called Heirloom, and they are working on basically finding. So there's actually a lot of capacity for CO2 in rocks that have not been exposed to these levels of CO2 for a millennia, and so people dig up these types of ultramafic rocks, they're called, and they can absorb quite a bit of CO2 by weight. Like I said, that process right now is slow, so companies like Heirloom are trying to get better contactors to basically try to, accelerate that process. And then you can just bury that rock and that CO2 should be permanently sequestered. Um, but the other ways are basically, to not have to wait all that time for something to mineralize is to pump it underground. So, not an expert in this, but basically taking spent oil wells and then pumping CO2 into them until they're like at those pressures are typically liquid form, and then that will very slowly mineralize over a few hundred years. People worry about the safety of that. CO2 is heavier than air. It's an asphyxiant. So, do we really want to be living near, a giant reservoir of CO2? That these are important safety questions I think that need to be answered. But those are some of the solutions they have to sequester CO2.
Yeah, that I feel like that was a fairly early solution that was floated, was kind of pumping emissions underground, but I didn't really know if that had been implemented, or they realized that there were some unforeseen consequences, um or what. But yeah. Speaking of, is there sort of, you had mentioned how the traditional way of condensing CO2 requires, a huge amount of energy. And so then you found this way around it using these redox carriers. Is there any unforeseen drawback to this approach?
It will take energy. I mean, regardless of what you do. Um, and then you will locally deplete CO2, right? So the idea is that you scrub it from air that you treat. And it's sort of like desalination has a similar problem, right? So you desalinate water for drinking and then you exhaust very salty water back and you have to worry about, the impact on marine habitats. And it's the same thing with the CO2. When we extract it, the air will be depleted, which shouldn't be a real problem in most places with diffusion, but it just depends on scales and things like that.
And there's, in terms of these, the redox carriers that you were using, those are pretty cheap and easy to find, safe to dispose of.
Yeah, they are actually. They're better than the amines that they use in thermal cycles right now, which emit a lot more toxic things that in their process that they have to scrub out.
Okay, interesting. And then I think you mentioned this with the HVAC, but just, the sort of wide scale implementation of this, kind of sounds like, instead of like having a factory that's job is pulling CO2 from the air, it'd be better for everybody to have like a little box on the top of their house or something like that. Is that kind of the?
We were thinking office buildings, so it's very interesting. Like I said, I've learned a lot about HVAC in the last year. Um, in order to keep CO2 levels down in a lot of crowded office buildings, they have to take in an enormous amount of fresh air because there's no way to lower the level without like just dilution with fresh air. And that has to be heated and cooled and climate controlled. And so a lot of energy in buildings is spent heating and cooling fresh air, which then gets quickly exhausted again. And so the idea is that if you can scrub CO2 from indoor air, you can recycle that climate controlled air, and then that you can save both on HVAC costs plus you're collecting the carbon from the indoor air. So there's a lot of benefits to that, which I think are pretty compelling. So even in the absence of a carbon tax, you can save energy on the building, which will help pay for the process. But then, of course, with the carbon tax, and you can also have a secondary source of revenue with your collected carbon.
And the source of carbon dioxide in these office buildings is people?
Yeah, 4%. You exhale 4% CO2 every time you breathe out.
So in an unventilated office, you would all end up suffocating one another just by breathing?
Yes, the ventilation is very important, and actually in classrooms as well. I'm sure in yours as well. Once you get to 800 ppm, people get sleepy. Above 1,000 can be dangerous. I joked around that, like, when you teach Gen Chem and the big, we have these giant classrooms, are people getting tired because you're bored, or are they just like suffering from high CO2 levels in the room? But it's true that, like, everyone exhales, I don't remember how many kilograms of CO2 a day, but it certainly in regulated office spaces, one of the main purposes of the HVAC system is to basically keep bringing in that fresh air to keep CO2 levels low.
And the idea is like, then you would have attached to this unit just a sort of thing that's condensing carbon into what, like a little rather carbon dioxide into like a little canister that you then remove?
Yep. Mm-hmm. Yep.
Cool. And what about, have you guys looked into application of this sort of idea to any other greenhouse gases, right? So another big one that's talked about a lot is methane in agriculture. Um, is there sort of any approach or a similar sort of approach there, or an avenue?
So it's a great question. I was just talking to someone that also works in gas operations, and so the other one, big one, is NOx, NO2, which is the third most significant greenhouse gas that's emitted by humans after methane and CO2. And these typically exist in parts per billion, and they're much, much, much more inert than CO2. And just having worked on that problem for a little bit, we've both realized that, for example, with methane, it is just better to try to plug up all the leaks in our pipelines than it is to try to recapture it, right? Just prevent the leaks from happening in the first place, because it's so hard to capture. And then the same thing with NO2, a lot of that's from agriculture, for example, and just by using fertilizer more intelligently, you can reduce the amount of NOx, and then from point industrial sources like nitric acid production, you can basically scrub it from there. So it definitely is better to go for it at the source than fight entropy and get it from the atmosphere once you've released it, it's parts per billion. It's very small.
So CO2 is actually kind of the easiest one, just because it's a little bit higher concentration and a little bit less inert of a.
Yeah, yeah.
And actually that kind of brings me to, like, what was the nature of that interaction between the carbon dioxide and your research in your redox carrier? I mean, did you
Yeah.
form?
Oh, go ahead. It's basically acid base. So if you bubble CO2 or if you breathe into a sodium hydroxide solution, you probably know, like, ocean acidification. Like, if you add CO2 into an alkaline solution, it'll react with hydroxide to make bicarbonate, right? So it's the same thing where an O minus in a phenoxide or something, or an alkoxide group, is also a nucleophile, and it will also just react with CO2 to make that organic carbonate species.
Cool. So when you have these research projects, you've collected your data, like, what timeline does a project like this take place on?
They can be many years. I mean, people spend their whole career studying a problem sometimes, or trying to refine their solution to a problem. It really, in the end, just depends on how long you want to keep doing it. I mean, for me, especially in the last few years, we've been much more interested in commercialization. So we've been trying to, like, target specific metrics for some of the things that we develop in the lab.
Yeah, I always found that to be a difficult part of research, was the writing papers when I felt like the project was not done or anywhere near done. You kind of got to sell it as this complete thing that I feel like still needed work, but yes. And so then how many do you guys have, like, as a lab, a target on publications per year?
No target. Funding agencies care, so we're aware of that. We have to get our grants renewed every 3 years or so, and so we want to make sure that when we submit that renewal, we're like, we did something with your money. We trained this many students and published this many papers and contributed to the literature. So those are the things that we think about.
Yeah, so I mean, I think that's, the big responsibilities of a research professor is, you have the teaching side, but in terms of your research, you have the fun part of research, which is actually doing the research, collecting the data, analyzing the data, but also the funding aspect as well. It's a little bit like running a small business, no?
Yeah, yeah, it is. It's a lot of different moving pieces.
And then, yes, and then in order to get those grants, you have to publish papers, because that's your way of representing that you are contributing to the field in a significant way.
Yep.
Cool. Well, so that's all the questions we have. Is there anything else you want to close out here with? Any update
Um,
on fun future stuff?
I would just say, like, it's exactly what you said. If you're looking for paid summer research in 2024, you gotta start looking for those chances now. They have lots of different programs available. Usually the deadlines are between January and March. And it's never too early to start. I mean, a lot of programs, some of them will take freshmen and sophomores, and so it was kind of game changing for me to do it. And at worst, you decide you don't like research, but you had a job for the summer.
Put on your resume, which is great.
Yep.
Yeah, I just reiterate that whole thing. I really don't know anybody that is currently employed in the STEM field who didn't get involved in undergraduate research at some point, because that really tends to be the stepping stone towards sort of a more to education. All right. Well, everybody, let's thank Dr. Yang for her time. Appreciate you coming and answering our questions and allowing us to study your research this semester.
Thank you.
Cool. All right. And so the last part of this is end of semester. You guys remember? Y'all completed a survey about how towards research. We have a follow-up survey that we're going to do now. Talk about. Did that cut out?
Yeah, I think you did.
Sorry, this microphone is really giving me trouble here. You got to hold it in just the right way or it'll cut out. But yeah, sorry, I was explaining the end of semester survey. Do you want to introduce this real quick?
I will, yes. Okay, so my name is Ira Clark. I'm an assistant adjunct professor at UCLA. And this whole experience of you studying the research of Dr. Yang this semester is part of a project that that I'm leading, that we have in collaboration with Fresno State, and Dr. Corsepius is part of the team working on this. It's what we call research deconstruction. We want to know how this has impacted your experience in chemistry this semester. What's worked, what hasn't, and also, how has it changed your perspective on science and science in general, chemistry in particular. So at the beginning of the semester, you took a survey that our assessment team, I'm not part of the assessment team, but our assessment team prepared that survey. They've prepared another survey for now the end of the semester to see, what's changed, essentially. You should have been emailed that survey within the last half hour or so. And it would have come from following email address, assessment@teaching.ucla.edu. Subject header should be short Chem1B, 1B survey. So please check your inbox. If you don't see it in your inbox, check your spam folder. There should be, in that email, there should be a link to a SurveyMonkey site. That's just the platform where the survey is being housed. The survey is voluntary, but we would really appreciate you participating in it. It'll help us understand how effective this project is, where we can make improvements, and it will help your fellow students at Fresno State in future semesters of Chem1B and perhaps more broadly. Your answers on that survey are anonymous. So there will be a question at some point that asks, I think, for your university ID number. That is so that our assessment team can match up your answers at the beginning of the semester with your answers now at the end of the semester. But I don't see anybody's individual answers. Dr. Corsepius never sees anybody's individual answers. None of the other project team members will, only the assessment team. And then they prepare an aggregate report that averages out everybody's collective answers, and that's what gets reported out. So, so your anonymity, in a sense, is protected. So please complete the survey if you can. Have you guys received the email? Are you able to find it?
Big no on that one.
A big no. Great. Okay. It's possible that there's been a hitch in sending out the email. In that case, I'm going to reach out to our assessment team, and we'll get a direct link to the survey, which Dr. Corsepius will post. Can you do that? Post it on Canvas, perhaps?
Yeah, no problem.
The class to, okay. So if you can take some time then after this link is posted to complete the survey over the next week, we would really greatly appreciate it. Thanks very much. Thank Dr. Yang and Dr. Corsepius for a really interesting session. I enjoyed listening to all of this.
Yeah.
I hope you guys have best of luck in your finals and an enjoyable and relaxing holiday season.
All right. Thank you very much. Have a good one.
All right. Thank you. Bye-bye.